So thank you all for being here. It's really an honor to come here and talk to so many people who are here to listen to me speak willingly. So this is my first time doing a lecture like this, and I've gathered from talking to a lot of people that this is not the first time most of you have been to one of these talks. So the way I understand it can run is either I can sit up here and jab, 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 and then at the end you guys can ask questions, or you could just interrupt me by putting up your hand in the middle of the talk, and we can make this into a bit of a discussion. And I absolutely do not mind the latter. So if you have any questions, or you don't understand something I said, or you just want to deviate me into another direction, please feel free to put your hand up. And unless I'm about to deliver a real zinger, I'm happy to stop and talk. Okay, so what I'm going to talk about is really little satellites and what they can do for astronomy. So before I begin, we have to ask ourselves, what is a CubeSat? And does anybody who does not actually work at LASP know the answer to that one? No? Really? Okay, great. Perfect. Because that means that I can use one of my favorite graphics about satellites, which comes to us via our friends in Canada, where they have helpfully taken all the different classes of satellites there are, well, not all of them, but many of them, and compared them to their nearest mass animal. So up top here we have the venerable RhinoSat. And for those of us who work on satellites, this is kind of what we aspire to in our career, the ability to put a rhino up in space and do some real hard science. And then it moves down the list, through all these different mammals down to the lowly duck class. And that's actually what a CubeSat is this lowly duck class. And it's pictured sort of here. It's a cube, hence the name. And the standard CubeSat unit is about 10 by 10 by 10 centimeters, or about 4 by 4 by 4 inches. And these were originally developed largely for educational purposes, to give a group of students a project to work on and maybe put a camera in and go up in space and take a picture of their house, that kind of thing. But then they started evolving into something that people started saying, hey, these are cheap to get to space. You just stick it in a rocket with something really expensive, and then when it gets up in orbit, it shoots out. Maybe we could start doing some science. And the neat thing about these CubeSats is they're kind of like Lego bricks. Okay, you can take 3 of them, say, and put them end to end and make what we call a 3U CubeSat, which is a little bit bigger. You can take 2 of these 3U blocks, you can put them next to each other and make what we call a 6U CubeSat, which is even bigger. And this goes on and on up to, the legend says, 27U CubeSats, but I've never actually heard of one being built. Anything above that starts to get, up here. And so this, this started to catch. Yes?
How big is 1U?
It's 4 by 4 by 4 inches.
All right, thanks.
It's a little bigger than that. Yeah. Where was I? Yes. So this has started to catch on scientifically in certain fields, especially Earth observing, because the Earth is nice and big and close and bright. You can do a lot of mapping of the surface. You can send up the internet things. That's one of the big things. It's also caught on scientifically for looking at the sun, because the sun is nice and big and bright and close. But for astrophysics, it's tended to be regarded What I'm going to talk about is the raccoon class. We are not duck class. We are up. I just broke it. There we go. We're up there. So for astrophysics, though, it is long broken down to this sort of mentality. And I say general consensus of the community 2013. It still kind of largely is. The idea is you want to build a satellite up here. You're building something scientifically interesting and useful. And down here, it's kind of a bit of a toy. Okay? And actually, I say specifically 2013 because at one point in 2013, somebody came to me and said, hey, are you interested in these new CubeSat type things? We could really do some interesting science. And I, arrogantly scoffed and said, you can't do science with a CubeSat. And now I'm here telling you about all the great science that we're going to do with CubeSats. So what ended up happening is about 4 years ago, NASA Astrophysics said, okay, we'll bite. I know that the community is uncertain about science we can do with these things, but we're going to fund a few and see what happens. And so to date, they have funded 5. And only one of these has actually gone into orbit thus far, called HaloSat. This was led out of the University of Iowa. It's been in space for about a year. It has produced science. It's very interesting. We're rooting for it. The rest of these are still in development stage, with 2 of them, which I'll talk about today, being developed here at LASP by our group. Okay, so why, might you ask? And I think these guys up here probably know the answer, but why, might you ask, would we scoff at such a small little satellite for astrophysics? And the reason is because we're not looking at the bright sun. We're not looking at the Earth close by. We're looking at these things that are really, really far away, and they're not producing a lot of light that we can easily see. So much like your eyeball, if you're in a bright room, your pupil gets really, really small because it doesn't want to let a lot of light in your eyeball to your optic nerve. But then you go in a dark room, your pupil opens up because it wants to be able to let the less amount of light in that dark room in so you can see. Well, it's kind of the same with astrophysics, except we're in a really, 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 really dark room, and we need the biggest possible eyeball that we can build. So here's a sort of a cluster of some of the large ground-based observatories that exist now in Hawaii and Chile and South Africa and other places. And then over here on the right, we have the really, really big ones that are being built now, culminating in this European Extremely Large Telescope, which is 40 meters in diameter. Okay, so that's half a football field as a big collecting mirror. And the idea is that these photons from astrophysical sources are raining down on the Earth, and these objects are so far away and we're looking so deep out into the universe that only a few of them are actually going to get caught by this big net. Okay? So the bigger you build, the better. Hence a small satellite being, Now you might be wondering, or you might have noticed, what about the most famous astrophysical instrument there is, the Hubble Space Telescope? It is on here. There it is. That little itty bitty thing down there. With its successor, the mighty James Webb Space Telescope, being this little itty bitty thing over here. Well, it's kind of hard to get big things in space. That's the punchline. So just to drive this point home, we tend to call these things light buckets, meaning it's a big bucket meant to collect light. And so I thought I'd put that in a little bit of perspective for you before we move on to more of the details. So if we take the EELT, the really big one, this is not a real picture, it's not built yet, this is a nice brochure picture, and we turn it into an actual bucket, this would be your Olympic-sized swimming pool, right? The real class, okay? And then if you were to say, well, how does that compare to something like the James Webb Space Telescope, this $9 billion wonderful thing that we're hopefully going to launch in 2 years? Well, that would be kind of like a nice quality above ground swimming pool. And I don't mean to disparage JWST. This is Backyard Magazine's 2014 #1 above ground backyard swimming pool you can buy. But even so, it's only about 2.4% of a net compared to this EELT. And it's collecting a lot less light. Okay? So let's extend that down to a CubeSat, and now you're actually at a real bucket. Okay. But interestingly enough, when I started this analogy, I started with the Olympic-sized swimming pool, and when I got down to this real bucket, I realized that this real bucket would actually carry more water than this real satellite. So it's even smaller than that. Okay, so why then, what's the first reason that you would then go and build one of these? Well, it's in space. Okay? So a ground-based telescope like the EELT, as big and beautiful as it is, has its limitations. And chief among those is it's down here. And the thing about down here is that we see the colors we see because it's one of these serendipitous regions where the air that we breathe happens to be transparent. And that's not really the case in most places. So here's the visible spectrum that we all see with our eyes, and that light happens to penetrate air very nicely, but air is a very complex thing. It's a whole bunch of different molecules. It's not just oxygen and nitrogen, it's carbon dioxide and methane and nitrous oxide and things like that. And all these molecules add up to be really, really efficient at absorbing light. So most of the electromagnetic spectrum generated by things out in space doesn't actually make it to us down here. And so there's a limited amount of astrophysics we can do in these holes, but there's a lot of very interesting things that we need to go out into space to do to get away from the Earth's atmosphere. And where I'm specifically going to talk about today is the ultraviolet part of the spectrum. And you're all probably familiar, okay, especially in Colorado. We got to wear our sunscreen to prevent sunburn. That's being caused by this little bit of the ultraviolet that manages to get through to a small amount. But where I'm going to talk about mostly is this region here that's really, really blocked by air and really does not get to the ground at all. And one of the reasons I like working here is, one, because that's where I fell in when I did my PhD and I got kind of stuck, but also because there's a lot of low-hanging fruit, because this is a really hard part of the electromagnetic spectrum to observe in. So much so that some parts of this region have actually been more or less unexplored. There's been instruments made that have gone into space, but they haven't been able to really fill in this hole, and we have a lot of, I don't want to call it low-hanging fruit, but almost low-hanging fruit available to try to go out and get if we can solve the problem for why this wasn't explored that much. And it was not a lack of scientific interest, it was a lack of technology. This is a part of this EM spectrum where all the atoms and molecules want to absorb light, which means that then you want to go and build a telescope, the things you build it out of don't want to actually reflect your light, they want to absorb it too. So, okay, so let's take a little break and look into the future. So NASA recognizes that this is part of the science spectrum that we are missing and that we want to go out and get. So a few years ago they commissioned some studies for some very large instruments, this was mentioned a little in the intro, that would be in the future. And one of them in particular, the Large UV Optical Infrared Surveyor, for which there was a public lecture here in 2018 by my colleague Kevin France, is kind of the most audacious of the group. It's the idea of putting an actual swimming pool-sized telescope out there. And this would very much be like a successor to the Hubble Space Telescope. It would be broadband, it would do a great many things. It would be a multi-purpose observatory. But one of its principal goals is to push into this region of the UV that we currently don't access very well. And it'll do a lot of other things like solar system science to almost the same level of certain early probes to the exoplanets. This is the Moon Enceladus orbiting Saturn, simulated. Imaging the cosmic web of material that spans between galaxies out in the universe. Really beaten to death galaxies themselves, which are big, complex objects that we don't fully understand. And of course, you know, the real thing that's motivating a lot of people right now, understanding all the planets that we're finding around other stars and characterizing them to determine whether they're possibly capable of supporting life. But the thing is, to do all of these things and to extend into the part of the UV that I want to talk about, we need to advance our technology. We are not capable of building this right now, going out and doing all of these things. And so one of the reasons NASA conducted these studies is to guide the pace of astrophysics technology development for a while to see if we could solve some of these problems before we ever start a mission like this, so that we can hopefully avoid cost overruns if we were to actually get to do it. So I'm not going to talk about this that much because Kevin France did. I will say there's a lot of cool information on the website, including some wonderful renderings of this thing, you know, coming. Yes?
You said you're not capable of doing this. Why not?
Well, we still have a lot of technological problems to solve. So one of the interesting things about the LUVOIR project is it wanted to only choose things that it's pretty sure that we can solve if we just focused our efforts on developing the technology to do it. So it's not so audacious that we have to invent fully new things. It's just we need to take technologies we already have and improve them a little bit here and a little bit there. Yes?
So you're saying the mirrors and the detectors can't handle UV? Is that?
We're saying that the mirrors are not good enough to do it in an effective way, and that the detectors would need to be scaled to larger sizes and to have maybe a little bit different bandpass efficiencies and more resiliency. They're really tweaks. But they're tweaks that probably would not have been done without this sort of guidance to really push it along. It's a trap that we didn't really want to fall into, of saying, boy, if I could invent this technology, it'd be really great. Let's do it in parallel with this large mission, and then if it doesn't actually work out, the large mission gets kind of stuck and costs overrun and things like that. So it's about solving these tweaks now and guiding the effort in the future. Okay. Let's see, where was I? Right. So these technologies are being developed now. But the problem is that even if this got approved by the Decadal Survey and endorsed by NASA and then endorsed by Congress and then started to be built, it wouldn't really come until about 2027. So I have this kind of crummy graphic coming maybe in 2027. There's a narwhal for scale, because obviously that's what we scale to. So what are we going to do in the meantime? Well, in the meantime, maybe we can take some of these technologies as we develop them and use them to get some of the accessible science that we can't do now with existing satellites, but we could do if we were to roll these into something just a tiny bit smaller. I'm sure there's a lot of technology in the Fruit Loops too. Okay, so what's one example? Well, does anybody know this artist's picture? It came out about this time last year. Super exciting, made all the news. Any guesses? Okay, so this is an artist rendering of the surface of a planet orbiting a star which has two companions that are kind of far away. Okay, this is a planet that was discovered around a star known as Proxima Centauri. Proxima Centauri is the closest star to our solar system. Okay, this is the type of thing that if you want to write a science fiction novel and have humans venture out into the cosmos for the first time, this is where you're going, even before there was a planet. Okay? And so when this was discovered, this was very exciting because this is a rocky planet, meaning it's small, it's kind of like the size of Earth, and it's orbiting in something that we call the Goldilocks zone or the habitable zone, meaning that it's orbiting a distance away from its star where the heat from the star is instant on the planet to keep it at such a temperature where liquid water might exist on the surface. So this is illustrated here with our solar system right here. So in the green zone is the good zone. You can see that Mercury, too close to the sun, too hot. Venus, kind of on the boundary. Venus probably had surface water for a while. In fact, there was a recent study that came out saying it might have had it even as little as 1 billion years ago. But then something happened. There was a runaway greenhouse effect. The oceans evaporated. Then the water vapor got dissociated, and then it escaped. Yada, yada, yada. Now it's the driest thing in the solar system. Then on the other side, we have Mars, kind of on the outside of this zone. Mars, as you know, might have had water. We're still studying. It might even still have water below the surface. A very interesting place to go study. And then right in the middle, we have the place we all know and love, Earth. Okay? So we've taken this, and in the past couple of years, we've discovered a whole bunch of planets around other stars, and we've started to discover these Earth-sized planets or so in this so-called habitable zone. And here's one such system up here with 7 planets called TRAPPIST-1, of which 3 are in the green zone, and about 2 of them are what we'd call Earth or super Earth-sized planets. Super exciting. Now you'll note though, all of these guys orbit their parent star well within the orbit of Mercury. These things are zipping around on the order of days. Their year is about a few days. Okay? And the reason why this habitable zone is so close in is because this star is a lot cooler than our sun. It's what we call an M-dwarf star. It's low brightness, it's not producing a lot of heat, so the habitable zone inherently becomes much closer to the star. And what's interesting is these are much more common than stars like our sun. Okay, our sun, we call it a G-dwarf, but we only call it that because the most massive stars in the universe are way bigger. But in reality, our sun is in the top 20%. It's a big star. Most stars out there are quite a bit smaller. These make up about 70% of the stars. And they're the easiest ones for us to find planets around because the way we detect planets is from seeing their effect on the star. And we can only really pick that up every time they have a year. Every time they either pass between us and the star, or every time they pull their star side to side as they orbit. And so being that these have such a short period, they're the easiest things for us to detect. And they're ultimately also the easiest things for us to then go and characterize. So we've been very excited about them, except there's a problem, as there would be. Time went on, and we started to say, after we've discovered a few hundred of these, we started to say, well, maybe this habitable zone is a little bit too simplistic. Maybe we actually need to do a little bit of science and think about this for a while. And one of the things that we thought up, and this is something that my colleague Kevin France, who also works here at LASP, does a lot of, is, well, what else is going on with this radiation? It's not just the temperature of the planet that matters. It also matters how the star and the planet interact radiatively. And this is a problem that falls solidly into this UV block. So in the black, we have what our sun does. You can see it produces a lot more over here than it does over here. And then we have a star like this, which produces very little over here and a lot more over here. And then the planets are much closer. Well, this radiation has a huge impact on the atmosphere of a planet. Okay? It can break down molecules in the upper atmosphere. It can heat the upper atmosphere and cause escape. It can do all sorts of things I'm not really going to go into. The point is it would be really nice for us to be able to do some really detailed models and determine whether these planets could actually be habitable. The problem is we don't have all this information. So Hubble, I'm going to drop the laser pointer for a second. Hubble can do some of this and all of this, but it can't do all of it, and you really need all of it to put into the models, and we just don't have the resources available. So this is the type of thing where we could build a new mission that might take 8 to 10 years and go up there and answer this, or maybe we could pick off a few choice targets and at least get some information from some sort of small satellite. Okay, what's the other thing CubeSats have? CubeSats have time. This is something Hubble does not have. Okay, Hubble is approaching 30 years old, and it remains, in my opinion, as an astronomer, the greatest scientific instrument in the history of mankind, humankind. It's, of course, that's my opinion. It's approaching 30 years old, and it is so oversubscribed that every year when the operators put out a call for proposals, they get more than 10 times the requests that Hubble can accommodate. And that number continues to grow year after year after year. Despite the fact that it's aging, people still come up with creative and new ways to try to use it. And what this means is that you have a problem. If you have a scientific problem that you're working on, and it takes 100 targets being observed to really answer it, to get the statistics to answer this problem, you probably can't get that much time on Hubble. So instead, you pare down your survey and say, well, I'm just going to ask for 4 targets. And that's great. Those 4 targets will be useful, and we'll do science papers and things like that. But it won't fully answer the question. In fact, it might even raise more questions. And so you end up not being able to complete all of the outstanding science questions because you've only got this one observatory and everybody wants to use it. So here's a couple of examples. This is the sun, and it's flaring. The sun is actually a pretty quiet star. But there are other stars, especially these little M dwarfs I talked about, which flare more often. And the way they flare changes their intensity in a way that's very scientifically interesting. But in order to catch these flares, you basically have to stare at these stars forever. And then just watch as they go, ooh, ooh, right? And that's something Hubble can't really do. So you could build a CubeSat, sit and do that. And lo, I have put a logo of one of the other CubeSats. This one's run out of Arizona State University, being built to do exactly this. And this is very important also for our understanding of planetary habitability, because these flares interact with the planet very intensely. And it's especially true when the planet is so close to the star. Another option is just mapping large extended objects. We've all seen beautiful pictures of galaxies. Maybe we all have astronomy calendars. Those are usually made using mosaics, so the Hubble can't image the whole galaxy at once. It images a little bit, and it maps it all out and creates this beautiful mosaic. You're not going to get necessarily beautiful pictures from a CubeSat, but you can get very scientifically interesting ones that Hubble might not have the time to spend mapping out all the galaxies it needs to, so you can have survey-type instruments just sit there and plot at the sky over and over again, and nobody's competing for their resources. And there's a whole host of other things I won't go into that you could do if you just had enough time in space to do. Okay, so just to summarize that part, I like the ultraviolet. It's great, but you can only go into space to access it. And because of limited technologies, we've been a little bit limited on all the things that we can do there, especially when we're talking about large extended objects like galaxies and things like that. So now I'm going to introduce you to our team. So this is the LASP. This is not our lab name. We don't have a lab name. But what happened is we realized a few weeks ago that we had grown from just 2 astrophysicists at LASP, because we are the laboratory for atmospheric and space physics, which is kind of a little bit more local than, say, galaxies, all the way up to 7 PhDs. And we decided that we were getting kind of big and maybe we should brand ourselves, right? So we're in the process of coming up with a name and maybe a logo and all sorts of fun stuff. So we've got 7 PhDs. We have 5 grad students now, with another one coming on in about 3 months, and maybe another one a little bit after that, and also a few engineers. And we mix together doing pure science. A few of us only analyze Hubble data and do astrophysics, to pure technology. Some people only really work in the lab and develop new technologies and instruments, to mixing the two together, which is really the way to go, is to tailor your technology development to answer the scientific questions of the day. And in addition to this, we also have, at the moment, a dozen undergrads working with us. So we very, very strongly believe you do the science, you do the technology, but you also do the education. So we've grown to quite a large group. And in the background, you can see this rocket continuously lifting off, because that's another thing we do. It's just a cool video. I'm not going to talk about it. We like to develop large instruments and put them on rockets and shoot them into space and then have them fall back down, and we pick them up and fix them and do it again. It's a great way to test technology. But I'm talk to you instead about our CubeSats. So the first one I want to talk to you about is adorable. Because it is. It's smaller than this computer. Anyway, so it's called the Colorado Ultraviolet Transit Experiment, and which stands for CUTE. And it is NASA's second astrophysics science CubeSat, and the first one to actually include a telescope. The one that went before that, HaloSat, was a background experiment. It flew and looked at all sorts of areas of the sky. And it's a collaboration between us here at LASP and then people from all over the world. We have Austria and France and Ireland. And so it's, it's a global team. And what it's doing is this sort of thing. So this is a star. And if you go back all the way to 1991, when the first planets were discovered around stars other than the sun, they were odd. They were Jupiter-like planets, but they were orbiting very, very close to their central star. Shockingly close, something that we hadn't really even theorized before. And they were whipping around the star very, very fast. And we kept discovering these things, and we started to wonder, well, is our solar system weird? What's going on? Why is our Jupiter way out there and we have these rocky planets? What's with these massive Jupiter planets in close to the star? Well, time went on and we discovered that no, actually these are weird and we're fine. But we were discovering them because they're the easiest thing to discover. You have a very large planet that passes between, here's a little illustration, that passes between its star and us. And when that happens, it actually blocks a little bit of the starlight, which causes the intensity of that star to go down. And so you can measure this, but in order to really detect the planet, you have to measure it a few times. So when the planet's zipping around the star every 3 days, this becomes a lot easier than waiting, say, a decade for Jupiter to go around twice, right? So they produce a larger dip for the larger planet, and they happen more frequently. So time went on, and now we've discovered a whole bunch of other planets. I think the number's over 5,000 now, thanks to things like Kepler, which was partially operated out of here, and now TESS is a new mission up there doing fantastic planet detection. And we've started to reach the point where we're saying, okay, we have now discovered so many planets that we believe that as many as half or even more of all the stars in the sky have them. Okay, these are not rare, they're everywhere. Even Proxima Centauri, the closest star to us. It's time to now start thinking about characterizing these planets and understanding them, not just saying how big they are and how far away they orbit from the star, but what are they? And ultimately, the golden goose, can we establish whether they can support life, as we know it at least. So that's the distant future. For right now, we just want to go back to the start and say, okay, what are the easiest planets to detect? It's these planets. So what are going to be the easiest ones for us to characterize? I'm going to go back just to show the full picture here. So you can see this planet has this beautiful blue tail coming off of it. So what's happening is it's so close to its host star that it's very, very hot. Because it's very, very hot, its atmosphere is actually kind of bubbling away. Not in a way that's going to dissolve the planet or anything like that, but it is creating this puffy extended atmosphere that is trailing away from the star. And the thing is if you remember, our atmosphere is transparent to us at the wavelengths that we see in our eyes, but not so at other places. Well, it's kind of the same here. You might not see this trail of gas with your own eyes, but if you look at it at the proper wavelengths, you might. And what that'll do is it'll cause, if this is what the planetary transit curve like this looks like at visible light, this might be what it looks like if you look at the right wavelengths, where this gas is opaque and that makes the planet appear bigger at those specific colors. So to illustrate this is some work that my graduate student did. Erica. Say hi, Erica.
Hi.
I did not know she was going to be here. That was very nice. So on the left, we have data from the Hubble Space Telescope. And you might say, wow, that looks kind of noisy. But it is, in fact, not noisy. All this little up and down is the effect of atoms and atoms especially, in the actual star absorbing light. So the starlight's being emitted, and then there's the stuff out here on the photosphere that's absorbing it and creating this spectrum. And what Erica's done on the right is she's taken this data and looked at it both when the planet is not there and when the planet is there. We already knew there was a planet. And you can see this dotted dashed line here would be the size of the planet. This is the radius of the planet divided by the radius of the star. This is what it should be, but at certain wavelengths, it's a lot bigger. And well, that's because there's something in the atmosphere escaping away that is absorbing light and making the planet appear bigger. So we'd like to do this with Qt. The reason why this was Hubble, the reason why we need something like Qt is this problem. So you need to capture this whole transit curve. So this is the whole time the planet takes to go in front of its star. It's about 2 hours to 3 hours, depending on the system. And you need to get the whole phase curve, it's called, so that you can really do the metrology of how it's shaped and how deep it goes. The problem is that Hubble orbits the Earth, and every 40 minutes or so it goes behind it, and it can no longer see. It's stuck behind the Earth. You can't see the target. So you get these gaps. So this is a Hubble orbit, this is a Hubble orbit, that's a Hubble orbit, that's a Hubble orbit. You don't have the full phase curve, so you got to go back and try to fill it in, and then there's an orbit, there's an orbit, there's an orbit. Oh, but we're missing this kink here. That's really important. So we got to go back and we got to do it again. And in total, this ends up being something like 15 orbits of the Hubble Space Telescope. That is expensive. That is a day. A day of Hubble when you have 5,000 people around the world with burning science questions trying to do this. So Hubble has done this, but they haven't been able to do it for enough targets, enough times. They haven't been able to follow up for variability. And all the systems we're seeing look different. And when we go back to them again 8 months later, they look different. And we just don't have the time available with Hubble to answer this question. So, prime spot for a CubeSat. So this is cute in CAD render form. It's not fully put together. There's a few things that are really important technology-wise here. One is everything over here. So this is what we would call the spacecraft. And 10 years ago, this would have filled up about to there. And there would have been only this little room left for a science instrument, which is one of the reasons why I might have scoffed. But through miniaturization, it's got a lot smaller. This little area here has a star tracker right here that looks at the field of view and tells you where you're pointed. It has a pointing system, these reaction wheels that, just like any other satellite, can point this thing to thousandths of a degree accuracy, so you can get your star exactly where you need it to be and hold it there. It's got radios to transmit data to the ground. It's got onboard storage. It's got sun sensors to tell you where you are. It's got a power board to regulate the solar energy and pass it out in a regulated way to your science instrument. It's got, I can't remember what else it's got. It's got a whole bunch of stuff. I should know. But because it's so miniaturized, now we have a whopping 4U available for our science instrument. And the other thing I want to tell you, and I'm very proud of this, although it seems so obvious when you say it, is historically, and astronomy is a very old science, historically, telescopes are round. Right? And believe me, we spent a whole at least 2.5 months during the proposal phase with a round telescope in our CubeSat. And then one day, I think we just kind of looked at each other and said, well, what if we made it square? So we did, and then we spent another month with a square telescope, and then one day we said, well, what if we made it a rectangle? And we did, and this is really important because this little rectangle captures 3 times more light than a circle would in the same sort of volume that you could fit in there. And it means that we don't have a lot of room left for everything else, but we've been very compact with our spectrograph back here, making it all fit. And we're kind of proud of this obvious solution. So here's an actual photograph. So this is Erica setting up this telescope for acceptance testing after we got it from the telescope vendor. And you can see a couple of interesting things. Usually telescopes, the mirror is mounted on some sort of plate that then you meter the rest of the telescope off of. We're not doing this here. We're metering everything right off of the mirror itself, so it's actually the main structural element. So there's the primary mirror and the secondary mirror. And we like to keep things clean because this is a spacecraft, so we built a little tent around this, and we're sending nitrogen in there. And here's that little spectrograph on the back. So this is very compact. This fits in the palm of your hand, and it's got 3 mirrors and a detector in it. It's almost cell phone quality miniaturized. So light comes in through a little hole from the telescope and hits this little fold mirror here, which is all of about 3 millimeters high. And the beam actually focuses here at what we call the slit jaw, and it goes through a slit which limits our field of view, and then comes out to a grating, and this is a very fancy grating. It's got lines on it to break the light into its constituent colors, but the lines are not straight. They're curved in a certain way to correct aberrations in our optical system. That diffracts the light up here to a little fold mirror, and then sends it down to a CCD detector that I've taken out of that's not in the picture. And what we've got going on down here is a little clever thing thought up by Erica. Is we needed to get a camera somehow to the slit, and we work on big systems. This is not so hard. But on this little tiny thing it was. So she actually got this little borescope camera, which is like if you've ever had an endoscopy or something. It's a snaky little camera that wiggles around or goes down your drain or something like that. And she stripped it down and was able to build a jig to maneuver it in there and get it in this tiny little hole. And it worked out. And then here's our detector on there. So it's angled here. It's this little CCD. We're working in the near ultraviolet, so it's actually, we can buy stuff commercially. The next thing I'll talk about, you can't. But this has to be cooled to minus 50 degrees, so we had to come up with a cooling system. That's not uncommon, but it was kind of hard to pack into this little tiny satellite. We basically have to pull heat off of this and then somehow get it to the side of the spacecraft so it can radiate off into space and cool down. So we've managed to get all the components in-house. It hasn't all gone together, but we've been able to measure them each individually, and we're very happy to say that it looks like this is going to be pretty much what we promised when we wrote the proposal, which would be about 4% of a Hubble, but that's with a mirror that's only about 0.3% the size. Now Hubble's not really optimized for the NUV, so it's not a dig on them. If they'd wanted to, they could have done a lot better. But still, in terms of performance, we're very, very proud of what it seems to be coming out of yet at a very small amount of cost. And most importantly, though, it has plenty of time. Down here at the bottom is some simulated data. We have some colleagues in Austria. They actually put in their own proposal to the Austrian government and got some money of their own to build us a data simulator and a data pipeline. And they've been generating fake systems and sending it through our performance data and showing that we can actually do what we think we can do scientifically. So that's really exciting. So Qute's pretty advanced. We're awaiting delivery of our spacecraft from a company right here in Boulder known as Blue Canyon. They've been the ones who have really driven a lot of this miniaturization of the spacecraft. We're hoping to get it as soon as Friday, actually. And then we can start putting our instrument together and integrating it in the spacecraft and doing all the testing we have to do so that we can ship it off to the launch provider sometime next fall and get it off into space in 2020. It won't go from the International Space Station, which is where this video is, but it's still a cool video, so I showed it anyway. Okay, now let me talk really quickly about the other one. So the other one is quite different. This one's called Sprite. It's led by me. The other one was led by Kevin France, my colleague. And we've got also a large team. This one happens to be all within the United States. We don't have any European collaborators. We did, but then right after we won, they moved to the United States, so not international anymore. And you'll notice our big gaping hole right here. So I'll just segue into that. This is Laura Murray. She's one of my favorite undergrads I've ever hired, not to take anything away from the others. And what happened was sometime around 2 years ago, we decided we wanted to have a media presence. Okay? We wanted to start being able to communicate our science better by having somebody come and help us make graphics and brochures and things like that that really projected what we do so we could communicate to both the public and to other scientists. So we put out a job ad to this TAM major, Technology, Arts, and the Media here at CU, and we got a stunning amount of people calling up and saying they wanted to come. So Laura came out and she interviewed, and I told her, well, I'm thinking of putting in this CubeSat proposal for something called Artemis. Okay, so she went home, and I got an email that night saying, I was really excited, I really want to work for you, so I made you this logo in one night. And I was like, wow, you're hired. And she was great. She actually worked with me on the proposal, which was very interesting, because usually we kind of work alone. And she did things like, oh, you know, this table and that figure, they're not color coordinated. You should, you know, it worked. It really made it look nice. And then we won, which is fantastic. And then about 2 months after we won, I got an email from NASA saying, I don't think you can use the name Artemis for reasons maybe no. And so you got to change it. And so I spent like 3 months trying to come up with a new thing. I was very attached to this. And we named it Sprite. And then it was like, okay, we need like a fairy logo. And 9 months later, we still haven't figured it out. And now Laura is advancing, and she's got a job, and you know, and I don't have a logo. It's very hard. Okay, so what's Sprite going to do? Sprite's totally different from Qt. Okay, Qt is finding a focused science case that we could sort of do now with the technology we have, but we just don't have the time. Sprite's going to say, no, we're developing all this new technology. Let's do something we can't do that's really hard, and see if we can do it in this little tiny satellite, and then prove to the world that it's possible so we can build something bigger in the future. So one of the science cases, and this was in my bio because this is what I did as a grad student, is searching for the sources of reionization. So this is something big that happened in the history of the universe. Way back in the dark ages, at the dawn of the universe, all the gas out there was neutral. And then at one point, some sources appeared, the first stars and the first galaxies, and they started ionizing these little holes until finally all the material was ionized. And this is really important for our understanding of how the universe formed and evolved. Hubble can only see to the end of this period. So one of the prime reasons the James Webb Space Telescope was put together the way it was to see the beginning of this period, because it's very important. So what we're going to do with Sprite is we're going to push this even more by looking for sources here, way far away from when the actual interesting physics happened. And the reason we're going to do that is because this is what one of these first galaxies that ionize the universe is going to look like. This little tiny red smudge. And while it's really cool to see these, the fact is that if you look at these up close, it's a lot more spectacular, probably without the dust though. And these galaxies are big, they're dynamic systems, all sorts of things are happening, and if we understand the physics of what's actually releasing this radiation that's ionizing the universe, we want to study them up close too, to understand all of that, so we can try to extrapolate it back as a proxy to this little red smudge. So that's what Sprite is designed to do. And this has been a problem we've been trying to do since the 90s. With pretty much every UV instrument that's gone up into space. And we had a couple of limited successes with something called FUSE, which was actually built as an instrument right here at CU, but not at LASP, with a couple of targets, but not enough to really answer any questions. And then in recent years, very recently, this is 2016, there's been about 7 or 8 or 10 really good successes with the Hubble Space Telescope, but on a very specific type of galaxy. Why has this been hard? Well, this is probably a little complex, but it's hard because this is a galaxy, and then right as you get to the point where this light is energetic enough to ionize hydrogen, it basically collapses in intensity. So this is already a hard signal to observe with a UV telescope, and then all of a sudden it drops by a factor of 2 if there's no hydrogen, but there's hydrogen everywhere. So the real signals we're looking for is this essentially 0 way down here. So we need to build a little tiny CubeSat that can do this, and that's tricky. The other thing we want to do is, this is switching gears, a second science case. A lot of things in the ultraviolet are near to us. They're large, extended, beautiful objects, and they're interesting to study as large, extended, beautiful objects, but we haven't been able to do that. All the instruments we've developed in the past have these little point source apertures that can basically say, I wonder what it looks like here, and I wonder what it looks like here. And then they try to put together a puzzle from these little windows that they can put in there. So we want to build a system that can more effectively survey these large extended supernova remnants and star-forming regions. And so that's where Sprite comes in. I didn't tell you the acronym. It's the Supernova Remnants and Proxies for Reionization Testbed Experiment. Yeah. No, I've seen worse. Okay, so we want to do this science, but we also want to take these new technologies that have been developed and we want to showcase them and say, here's what they can do, but also they're ready. Okay, NASA is risk averse. They do not want to spend $200 million or $10 billion on something that isn't going to work. So they very much want to fly something they absolutely know will work. So we were lucky enough to be involved in the LUVOIR study. We did the UV instrument design and concept right here at LASP. It was a lot of fun. It took a long time. So we're tuned into these technologies, and we want Sprite to basically showcase the ones that are really important for the UV. First and foremost is we need mirrors that actually reflect light as opposed to absorb light. For the longest time, the best we could do is about 60%, which means every time you put a mirror in your system, you lose 40% of your signal. And so we started designing things with 2 mirrors. They made really bad images and really bad spectra, but we were able to do science. Okay, so long story short, working together, and this was actually the first thing I did out of grad school with some people at Goddard and JPL, problem kind of solved. Okay, so Sprite's going to fly those. Second thing we need detectors that are a little bit better than the ones on Hubble. We need them to have a lower background. Background's really important. If you want to see something really, really dim, you want to be able to stare for a really, really long time and not have background build up and overwhelm your signal. So these little detectors is a small version of a new type of microchannel plate photon counting detector that we want to stick in this little CubeSat and fly. So these are both essential technologies. There's a few other little ones that I won't really talk about. These are the ones that really drive the performance to being kind of above and beyond things that have gone before. This is brand new. I got my first dollar June 28th. So I haven't had time to make any nice CAD models or anything like that. But this is what it looks like in Raytrace form. So light comes in, hits our rectangular mirror, much like Qt, focuses on a slit, much like Qt, has a really fancy grading, much like Qt, a little fold mirror, and then the detector. Looks a little different when you stick it in the spacecraft. It's very space constrained. You might say there's a ton of open room here, but we need electronics to run the detector, a high voltage power supply, anti-coincidence shielding power supply and circuit, a flight computer, and yada, yada, yada. This is about 3 inches by 4 inches. So all that stuff gets to go in there. I have a very talented electrical engineer. He's going to take care of it for me. But when we put it together, we get a really impressive result. And this is a tiny bit optimistic, but it's not super optimistic. So without really going into the numbers, Sprite is projected to be as good, if not better in some metrics, than things that NASA has flown in before that cost $200 million for more like 4. Especially in pushing the and in multiplexing and getting a lot of spectra at once. Part of the way it does that is since it has a lot of optical elements, it's capable of taking nice tight spectra, I won't go into the details, that limits the background when you extract it, which is very important. And so we can take data that exists, for instance this galaxy I showed earlier, we can fold it through what Sprite's expected to do and find out that yeah, we can take this galaxy discovered by Hubble and we can see it even better, although it takes us a day, even though it only took Hubble an hour. But Hubble doesn't have the time to do this enough and to the right types of galaxies to really make these discoveries. And we can map supernova remnants too, which is great. This is one of Laura's figures. I just had like a plot and said, look, we can do it. And she said, no, got this. Okay, so in summary, I'm done. Where do we go from here? Well, I hope that I've shown you 2 cases where CubeSats can actually do some meaningful science. I think they can do meaningful science, but the community is still very skeptical. Right? These are very small little devices. So we need to be successful. So here's this slew again. HaloSat has probably already been successful. It's great. Qute's going to go next. I very much hope it's going to be successful. Then we have Sparks at the University of Arizona, something called BurstCube from Goddard Space Flight Center, which is really a technology test experiment. So this one should be okay. And then Sprite. And then what do we do in the future? Well, we need to keep our eyes out for what comes next. So NASA Astrophysics is always identifying the technologies it thinks are the champions of the future, and they get developed, often very successfully. So we keep our nose to our ear to the ground, pick these up and try to bundle them into sort of the next thing to showcase these things. Because to build an orbital instrument, you have to take this technology through so much ground qualification before you can get it in a satellite mission that takes 8 years to make and costs $250 million, and we only build 2 or 3 of them a decade. Or we can demonstrate them in these CubeSats and say, look, this is really great. We can do something fantastic. Let's do it now. And that's that. So that's my talk. Yes?
What kind of redshift is Sprite working in, say, compared to the Hubble Ultra Deep Field?
Well, the Hubble Ultra Deep Field is trying to look back to the end of the epoch of reionization. So it's going back to redshift 6, as deep as redshift 10, which is, if you think in terms of years, that's the universe is about 13.6 billion years old. That's looking back to when it was 13 billion years old. Sprite is looking close to home. It's looking at from 0.16 to 0.5. And the reason why is because the 0.16 is the smallest wavelength you can get for the ionizing edge, which is at 912 angstroms, to be redshifted to above 1020 angstroms, which is where Sprite's mirror coatings start to reflect light. So they don't actually reflect all the way down to this hydrogen ionizing edge. This is really hard territory to work in because absolutely everything in the universe wants to absorb light at that wavelength, pretty much. So that's the minimum it can work at. And then it limits out at 0.5 because that's where Lyman alpha, which is a very interesting line to pick up scientifically, shifts off the detector. So you kind of want both together. So it's very much the local universe, but not as local as you'd really want to go. But we can't get there because we don't have that technology yet. Well, we can, but it's not good technology. Anybody else? Yeah.
What is the design lifetime of these CubeSats?
Good question. So NASA, in the proposal, these are very low budget. So Astrophysics has actually capped one of these CubeSats at $5 million. Both Qt and Sprite are under that. We kind of went cheap. They And so they don't want to have you say in your proposal, this has to last 2 years to get my science. They want to see nice, succinct, tight science cases. So that sets the lifetime at a year or less, notionally. Physically, if you get a high enough orbit, if you're not going from the International Space Station, you can get up to 500 kilometers or higher of an orbit, they could last 3 to 5 years. Your electronics might break down before that, might fail, but you could conceivably get 3 to 5 years out of one of these pretty reasonably. And then you just, keep working it, keep getting your science, and maybe NASA will give you money to analyze the data, but really, at that point, you can do it anyway. We actually run these things right here in this building. So LASP has built a lot of CubeSats, but for heliophysics and for Earth observing and other purposes. Like I said, these are just 2 of the first 5 for astrophysics. And they're all controlled from a room upstairs. All the data comes down here. We have a radio dish or a radio receiver up on the roof and another one up in Fairbanks, Alaska. So we're set up to do this ourselves, which is really nice because it actually costs hundreds of thousands of dollars to do it through contract with somebody else. So we can operate it as long as we want.
So what kind of orbit are you looking at to put them in?
Good question.
More polar or more equatorial?
Both. So Cute is manifested to go into a sun-synchronous 10 a.m., 10 p.m. orbit. So it's going to go pole to pole, almost pole to pole, which is wonderful for Cute because that allows it to look at its targets for the longest amount of time with the least amount of Earth blocking. So one of the reasons Hubble has a hard time filling in those transit curves is because it's constantly going behind the Earth. With a sun-sync orbit, for some targets, we can actually stare at them continuously. If they're a little bit inclined, we still lose them for a little bit of time, but not nearly as long as we would if we were doing an equatorial orbit. Sprite, on the other hand, space is actually really bright at this one wavelength right here, Lyman alpha, and a few others too. So there's like a cloud around the Earth of hydrogen. It's being excited by solar wind and et cetera, and it produces a very bright signal at this wavelength, and it gets brighter in the daytime than it does at night. So with Sprite, we really do want to be occulted by the Earth, so we can get on the night side when we do our scientific observations and drive this value down. So we don't want to go into a sun sync because then it would be too intense. So we'll be probably going on an International Space Station launch, but in a Cygnus system that ejects some CubeSats to higher altitude. So it's the main spacecraft stops at the space station, and then this pod jettisons out and goes to a higher orbit. Yes.
How do you keep your CubeSat pointing in a consistent direction?
Well, that is the magic of the satellite provider. So they have, Blue Canyon has really done a fantastic job, and I visited their lab, of making a reaction wheel system with 3 reaction wheels that's about that big. And these wheels spin and they produce an angular momentum, which then moves the spacecraft and points it. And they can achieve 6 to 7 arc second pointing stability pretty easily, and they've demonstrated as low as 1.6. I've heard, which is really fantastic. These telescopes are pretty small, so they actually max out at about 5 to 6 arc seconds resolution anyway. So if you can get below that, you're not really contributing too much to the noise air. So we'll see how it actually performs on orbit. We need it to be less than 7, but they do it, and they've done it quite often. And there's been satellites built here at LASP that have used these that have demonstrated better than that. So. That's one of the things that really enables these kinds of missions, is having that kind of pointing system. Yeah.
How do you launch these into higher orbits? Do they have little thrusters on them? Or
These don't, but there are a lot of research being done by NASA and other people in developing miniature thrusters for CubeSats. Some of them are electric propulsion, some of them are chemical. The idea for those is not really, although I think it's been done, orbit transfer within low Earth orbit, but more like getting on the SLS engineering launch. There's a program to put a bunch of CubeSats on that and go out towards the moon, but then to enter moon orbit or to go to someplace else, they need their own propulsion to do an orbital insertion or to go where they're planning on going. So they're trying to miniaturize sort of a 1U module that would be capable of a certain quantity of delta V to get into orbit or to the proper orbit for that science. We don't need that. We rely on the rocket that we deploy on getting us to where we need to go. So in the case of Cute, it's actually possibly Landsat 9 launch. We'll have a ring that'll have a bunch of CubeSats. It'll go into polar orbit, and it will eject us at some point in time in the trajectory to our orbit. For Sprite, we don't know what our launch provider is, but as I said, they've developed this system for the Cygnus resupplies to the space station that has a little ring module that takes all the CubeSats with it to a higher orbit, and then once it gets there, it ejects them into that orbit. So that provides the propulsion for you.
So they're just like spring-loaded?
Yeah, they have a little deployment canister with a little bit of outward pressure, and when the door opens, out they go. It's very much like the video I showed for those little ones being deployed from the space station. So there was a CubeSat built here at LASP called Minx that went from the space station, and I think there's a YouTube video of it being deployed. It was really pretty cool that they got that. And it just sat up there until it was ready, and then the astronauts did their thing, and they pushed the button, and out it went.
What do you mean by 1U and 4U for the size of these things?
Yeah, you guys, you came in late. So a CubeSat originally started out as a little educational invention, and it's about a 4-inch by 4-inch by 4-inch cube that they found out that you launch these rockets, and sometimes, especially with like a Falcon 9, that's really egregious. The Falcon 9 has a huge payload variant. It can accommodate a gigantic satellite, and most of the time what launches in there is like the size of this podium, okay? And actually probably a little bigger. So you have this massive amount of empty space, and it's still going up there. So as long as you can have the mass available to still get to your required orbit, you can put more stuff in there. And so they started putting these little CubeSats up there for education, for letting people build their own things, and then slowly they started to become a scientific tool too. And what you can do with these little CubeSats is it's basically the discrete measure. So you start with this little 1U, which is that 4 by 4 by 4-inch cube, and then you can start putting them together in essence to make bigger things. So Sprite is and Cute both, wrong way, is a 6U. So this down here would be 1U, and then if you could sort of replicate that here, there'd be your 2nd U, 3rd U, 4th U, 5th U, 6th U. Okay? And these things go up to as high as 27U. And then after that, people just start building satellites. Yeah. So it's just a convenient way of describing the size and format. Anybody else? Yeah?
For Cube, what are your major sources of noise? You mentioned for Sprite you have like air glow and Lyman alpha.
Yeah. So for Sprite, this is actually all the noise down here. So there's the detector background, which is incredibly low. We use one of the other technologies we're flying is something called anti-coincidence shielding on the detector. And so the largest source of noise on these sorts of detectors is actually particles flying around in space, charged particles, and they zip through the detector, and when they go through, they create an event like a photon had come in. But then they also come out the other side, and so we put this scintillating material around the back. And so when the particle travels through the scintillating material, it actually lights it up. And we have a little other detector that detects that light and says, hey, this happened at exactly the same time that happened. It's probably a particle, it's not really a light. So that's a cool little trick. And so that knocks us all the way down to here. Now Cute, and then this is grading scatter, which is just model of how gratings work. Cute, though, is using a CCD detector, and I'm personally not an enormous fan of CCDs, but they are easy to get a hold of at least. I don't like cooling things. What a CCD does is it has an intrinsic dark rate, so you can knock that down by cooling it. But you end up reaching a floor at some point in time. So every once in a while, the longer you sit there and collect light in these little potential wells on the CCD, this dark current sort of spits in there random electrons that get stuck in the wells and end up reading out like photons at the end. So that has a floor, and that's an event per time. So the longer you sit there and collect light, the more of these accumulate, and then when you analyze your image at the end, you've built up this bigger dark signal. And then there's also what's called read noise, which just means to actually read out each one of the pixels on the CCD, you shift them through this register, and as you do, you pick up charges that produces what's called a read noise floor. So you kind of have this sort of floor, except in a CCD it'd be somewhere up here. Just every time you read it out and generate an image. Your phone does the same thing, you just don't notice because it's taking a picture of bright stuff. But when you're trying to look at 10 photons, you notice that pretty bad. Yeah. Yes?
So I think it was on the Spark, you showed kind of a graph with your target and everything, and you had something in reference to cosmic rays. Is that something you have to filter out, or?
Oh, I know which one you're talking about. Yeah, that's cute. There we go. Right, so cosmic rays are charged particles coming at high energy from out in space. And they actually make it down to the Earth. You hold out your hand, one's going to hit you probably every 20 seconds or so. You don't really notice, although it actually can damage your cells, but only a little bit, and it happens all the time. But these very sensitive detectors like a CCD, they pick them up all the time. So in every astronomical instrument with a CCD, you take a 5-minute exposure of something, and you're going to resolve out the data and look at it, and you're going to see these blasts of light popping up as spots all over the place. They're pretty easy to take care of. If you take, say, 3 images in a row of the same thing, you can just say, hey, this is different between image to image, must be a cosmic ray. But sometimes they get really annoying and they land right in the middle of the most interesting part of your spectrum at exactly the most interesting time, and then they're a pain, but there's nothing you can really do about them on a silicon-based device. They don't actually interact with the type of detector on Sprite, so I'm not worried about them at all. Yeah.
You showed the cooling device. Is that thermoelectric or LUVOIR?
Yeah. So I guess what we have is we need to get the back of the CCD down to minus 50 degrees, which is pretty cold. And it's hard to deal with heat in space. There's no air. You can't run a fan, things like that. So if your electronics are dissipating a watt, well, that watt just continues to build up unless you find a way to sync it to something to take care of that. It just gets hotter and hotter and hotter and hotter. So we need to get this very, very cold. So we use this thermoelectric cooler, which is designed to shift heat from one side to the next side to the next side. So you end up with a side that's going to be cold and a side that's going to be hot. But if you let the hot side get too hot, then it stops keeping the cold side cold. So what we do is we attach a graphite strap to the hot side of this that we then move over to the side of the spacecraft where we have this. Ooh, it's fine. Where we have this shiny radiator panel which looks off into deep space. And when the way physics works, when you have this warmed up radiator panel looking off into something much cooler, it emits a bunch of infrared light, which is heat, out into space. So that's how we dump things. So we basically have to a thermoelectric cooler pulls heat off the CCD, and then we have to conduct it to the side of the spacecraft and shoot it out into space. And if we can keep that radiator panel to about 0 to 5 degrees Celsius, so about freezing, then this whole thing works. If it gets above that, then it starts to not work as well. So that's something we have to do a lot of analysis on.
Did you actually look at, say, I mean, it's designed for astrophysics stuff, but can you actually look at Venus and see if the atmosphere during a transit can
we would never point it at the sun.
right?
It would just explode. I'm pretty sure that's what happens when you point at the sun. It's just what I've been taught.
Or maybe Mars, so on the other side, but not at the sun, but at the planet.
We actually have this shutter here. When you read out CCDs, you need to turn off your light source, but the shutter is also designed so that when we lock up, which CubeSats do all the time, they're not flight-like electronics. A big cosmic ray can come in and hit something and cause a transistor to get locked up, and everything goes into safe mode, and we have to turn off and turn back on again, which is the way you solve all problems. But we've got it set up that when this happens, that shutter closes, because we might start tumbling, and if we tumble and look at the sun, it could completely cook our system. I mean, you're focusing, it's like a magnifying glass on an ant, except this is even bigger. So we don't want to fry our system and destroy it. Not only in the sun. Mars is pretty bright too. I don't know, I'd have to run the numbers. But to really see that atmosphere, you need a background source. You need something that the light from the atmosphere could occult. And Mars doesn't, have a lot of atmosphere. What's that?
No backscatter? So sun.
Oh, I don't know. I'm sure there's some planetary scientists in here who could answer that one. Maybe. Maybe not. We'll look into it. Anybody else? Okay, goodness.
Thank you.
much.
No, thank you guys. It really was nice.